Good afternoon, everybody. Hope you're all healthy and safe at home. Let us continue with our chapter 4, bounded linear operators. So in the previous class we had studied or we had discussed about the definition of bounded linear operator and stated some notes related to that. So in this lecture what we are going to discuss is we are going to discuss a theorem which which gives us a property of the L of xy, that is the space of all bounded operators. So let's see what the theorem states. Theorem 4.1.1. Let x be a normed space and y be a complete normed space, then L of xy forms a complete normed space. So we had seen that L of xy with the norm that we had defined in the previous lecture, it forms a normed space. Now when will that be complete? It will be complete when the space y is complete. That is the only condition that is required. X is a normed space and y is a complete normed space. Then we can show that L of xy, that is the space of all bounded linear operators, are complete. So we can show that. Now I had mentioned that continuous factor, so we can also see that in the following remark related to this theorem. We can prove that if it is bounded, then it will be continuous. So L of xy is actually the collection of all bounded and continuous linear operators. So let's see how we can prove this theorem. So for that what we'll do is we shall consider so we need to show that the other space L of xy is complete. So for that we need to show that any Cauchy sequence will be convergent. So let's choose a Cauchy sequence. Let an, where n varies from 1 to infinity, be a Cauchy sequence. Okay, let it be a Cauchy sequence in the normed space L of xy. Now we need to show that this is convergent. So as it is Cauchy's, what we can say, for m comma n greater than or equal to some capital N and some epsilon greater than 0, we have, what is the condition? Norm of an minus am will be less than epsilon. Okay, now with the help of this we shall show that the sequence an of x is Cauchy's in y. Clearly an of x means an is an element in L of xy, means it is a mapping from x to y, right? So an of x will be an element of y. Clear? This is x. So let's see now what will happen to norm an of x minus am of x. Now this is nothing but norm of an minus am of x. So for you people, if you need more clarity, this is actually the norm on y, right? Because an of x and am of x are all elements in y. So this is equal to an of x, an minus am of x. Now what is an minus am of x? Again I am going to apply an inequality here, that is this will be less than or equal to norm of an minus am into norm x, right, by the property of linear operators. Now norm of an minus am, we had seen that it is less than epsilon, so we get that this is less than or equal to epsilon into norm x, right? So we can conclude that for every x belongs to x, the corresponding sequence an of x is Cauchy's. And where will it be Cauchy's? It is Cauchy's in y. Okay, and y is a Banach space. As y is Banach or complete, we can say that the Cauchy sequence is convergent. So sequence an of x is convergent. Okay, so let us suppose that an of x converges to say some a of x. Suppose an of x converges to a of x, or I can write this as a of x is the limit of an of x, limit n tending to infinity an of x, right? So I hope this much is clear. Now what I'm going to show is, I'm going to try to prove that this a, that is the limit of this sequence, is bounded operator. I'm trying to prove that. So if it is a bounded operator, then it will be an element of L of xy, right? So let us see how we can do that. Now norm of a of x, and this norm is corresponding to norm y. This will be nothing but norm of limit n tends to infinity n of x, right? Now we know that norm is continuous, we have seen that, so limit can be taken outside. So limit n tending to infinity norm an of x. Now this limiting value of norm of an of x will definitely be less than the supremum of an of x, right? Norm an of x. Now again here we can apply the property of linear operator, that is this is less than or equal to supremum norm an into norm of x, right? So what we get, we know by the definition of the norm a, that is norm of any linear operator, was defined to be supremum of an of x, a of x. So here it will be supremum a of x by norm x, right? Now norm a of x is nothing but this is less than or equal to supremum norm an into norm x by norm x. So norm x and norm x will get cancelled, so I get that norm of a, this norm of the linear operator a, is less than or equal to supremum of the linear operator an. Now we had chosen this an to be an element of L of xy, right? So it is a linear operator which is bounded, right? So if it is bounded, I can say that this is less than some finite value, therefore a becomes a bounded linear operator, and hence we can say that a is an element of L of xy. So we have shown that any sequence, if we had chosen any sequence an in L of xy, with that help of that Cauchy concept, we showed that an of x, an is a sequence in L of xy, that is, it is a bounded operator. Then corresponding to that Cauchy sequence, an of x forms a Cauchy sequence in y, and as y is complete, we get it is convergent, and we have shown that the limiting value, that is the linear operator a, forms a bounded linear operator. Now next what we are going to show is, now we have not actually shown that an is convergent, we have shown that an of x is convergent. Now we need to show that an is convergent, right? And what we are going to show, we are going to show that an is actually convergent to this operator a. We shall show that an is convergent to the operator that we have obtained a, and clearly a is L of xy, so we can say that it is convergent to a point in the space L of xy itself. Now let's see how we can do that. Now we have seen that as an was Cauchy's, we have seen in the beginning that norm an of x minus am of x is nothing but it is less than epsilon into norm x, right? Now let us see for any x such that we are using a property that norm x is less than or equal to 1, what we can say, we have the above inequality becomes norm an of x minus am of x will be less than epsilon, because norm x is less than or equal to 1, right? Now in this case, what I'm going to do is I am letting any one variable, that is m or n, I'm choosing m here, letting m tends to infinity. What do we get? This am of x will tend to our a of x, right? Tends to a of x. So for so what do we get? We get so we get norm an of x minus a of x is less than epsilon for x belongs to capital X, such that norm x is less than or equal to 1. So we have obtained that norm of an of x minus a of x is less than epsilon. So now from this, how we can say that an is Cauchy's? So we know that norm an minus a of x, from that inequality we get this is less than epsilon. So from this we can say that norm of an minus a into norm of x is less than or equal to epsilon, or I can say that norm of an minus a is less than or equal to epsilon, as we have chosen x such that its norm is less than or equal to 1. So therefore from this, what do we get? We get that an is convergent. So we had chosen an arbitrary sequence in the space L of xy, and we have which was considered to be Cauchy's, and we have proved that this sequence is convergent. So this is how we shall prove the theorem 4.1.1. If x is any norm space and y is a complete norm space or a Banach space, then the space of bounded operators from x to y forms a complete normed space. So that is for the theorem. And next, there are many remarks which I would like you guys to work out, since the first one I had stated earlier, that is, if A is a bounded operator, then it is continuous and vice versa. Then we can easily show that kernel of A is a closed subspace, and also for any normed space X, the dual space X star is complete. Now why is that the dual space is complete? Dual space is actually the collection of all linear functionals, right? That is a mapping from X to R or C, and clearly R set of real numbers or complex numbers are all complete, right? They are Banach spaces. And so by the theorem, previous theorem just now which we have discussed, that is, if the mapping X to Y, Y is complete, then the space of all bounded functions, bounded linear operators L of xy forms a complete space. So here since we are considering X star, that is the collection of all linear functionals on X. Linear functional means it is a mapping from X to R, right? R or C. So R and C are both complete. So by theorem 4.1.1 we can easily prove this. Actually the proof is that, nothing else to prove in that. So we can say that the dual space is always complete. And also there's one more thing, that is if x, y and z are Banach spaces, and let A be a mapping or linear bounded operator from x to y, B be a bounded linear operator from y to z, then clearly BA will be a bounded linear operator from x to z. Clearly BA will be a mapping from x to z, that is clear for us. Now it is also true that it will be bounded, and its bound will be, it will be less than or equal to norm of B into norm of A. Now the third note or third remark, which is, we have already proved it. The first one, the second one and the last one are pretty much simple. I would like you guys to work on it. So that's it. we shall wind up today's session. Thank you. Stay home and stay safe.